So as you see, I have a wireless, I have a web camera here just to do some recording. As you may have seen, first of all, that you're welcome to the second astrobiology workshop. It's a workshop organized together with by Nordita and by the Finnish Astrobiology Network. And it's a pleasure to do this because it enhances certainly the way how we can interact with each other. From the Nordita point of view, we try to get as many people as possible to our various meetings, but of course there are people within the Finnish astrobiology community or other scientific and related communities which for them it's much easier of course to come to a meeting if it's locally here in Finland, and so we have therefore a lot of people from Finland this time. As far as Nordita is concerned, Nordita is a Nordic research institution which has some staff of 6 permanent people only. It's a relatively small organization, but it has something like 8 assistant professors who are hired for up to 6 years, and we have a postdoc program that is for Nordic people only, Nordic citizens, and it can have up to 14, sometimes up to 14 postdocs. In addition to having postdocs from the Nordic countries, Nordita is also having meetings, of which this is one of them, but we are also having projects among a larger range of different opportunities, but the project is one way of getting some activity started between the different Nordic countries. And it is desirable that something larger can perhaps follow up on that, like for example like a Nordic network could be initiated at a later point, which would then no longer be funded by Nordita, but could be funded, for example, through NORFA. NORFA is a big Nordic funding agency, and there's other possibilities to get money for that. So this is the second meeting of this kind. The project started in January this year, and we plan to continue this project for 3 years altogether. The next meeting we anticipate to have in January next year. Obviously, a number of people couldn't come to this meeting, and a few thought they could come and had to cancel in the last moment. So I hope very much that at least those people who wanted to come and couldn't come will be able to come to Copenhagen next time. And I think the next meeting should be in Copenhagen. And then, of course, after that, I don't know yet. But that's at least one possibility at the moment. Okay, so I think everybody has got their name tags and has got started with other formalities. And with these words, let me then give the word to Harry Lehto, who is the organizer from the Finnish Astrobiology Network. He also knows about all the local issues, and regarding housing, for example, that's another issue that we will discuss at a later point. But all the other issues, please direct directly to Harry then. As far as the program is concerned, the idea is that we should always have enough and very much time for discussions, journal discussions as well as discussions related to in particular presentation. So I hope you will very much make use of that, and if you are not, or when any one of you is not satisfied with the way how we are doing things, please let us know, and we hopefully have a chance to adjust things so that the majority of us will find this a useful event. So Harry, please.
Dear participants, I would like to welcome you on the behalf of the local organizing committee and the FAN. The local organizing committee here consists of Kirsi and Chris. So if you can get hold of me, or I seem to be too busy, you can also ask them about various local questions. Now in your small package you got, there is a map of Tuorong. which can be quite useful. We are located on this map in building number 6. So that's 6 is auditorium. Then number 1, up and right, is called Majatalo. That's the place where we're having our meals, lunches and dinners. Accommodation places are shown to you by the Majatalo group. Then the observatory is kind of schematically drawn to the right end of the map. This is observatory here. And then two, or actually 3 important other places. First one is the sauna by the sea there. That's number 28. That's sauna number 1. Call that number 1 here. And that's going to be tomorrow night and day after tomorrow. And tonight we're going to have sauna in building number 6. No, sorry, in building number 1. In the same building as the Majatalo, but seen from here, it's kind of on the back end of the building. You'll see where people wander around there. That's where the sauna is going to be tonight. So that's not going to be by the sea, but this is a little bit closer to the sea. Then number 27, which is all the way at the bottom here. That's for the harbor. There's a couple of rowing boats there, and then the long row boats are going to come also there. And that's where we're going to take off for our trip on Saturday. I think those are the main important areas on this map. If you have any other questions, just feel free to ask. Okay, in the registration package is the map of Turku, program, and 2 papers. One is by David Field, Astronomy and Astrobiology. What is astrobiology? Seems to be a nice summary. And then in Finnish, all of you who don't speak Finnish can try to learn some Finnish from this. This is a magazine that's targeted to mainly biology teachers, and it's a special issue on astrobiology, and this came out about a month ago. A special issue on astrobiology. Okay, then, in case you need to get in touch with me any time of the day, I'll give you my phone number, which is 050-358-6062, all on one line. Feel free to call any time of the day if you need. Okay, I think that's everything for the introductory part. Next one?
Yes, coming.
It goes. You can turn the lights off a little bit. Okay, so I'll start first talk here, and it's going to be about the Iceland Bioastronomy meeting. As the name says, it's bioastronomy, slightly different from astrobiology. It's more astronomy oriented, and it was held under the IAV Commission 51, which was just about a month ago. And Torstein was the head of the LRC on that one. It's a pleasure to have him here. And Reykjavik is a nice city. It looks like a small town, but it's actually quite big. About the size of Turku, but there are not really high buildings there. The meeting was quite intensive. For five days of talks and posters, over 100 posters and about the same number of talks. And the program was from early morning to late evening. Late evening. Sun sets really late in Iceland, as it does in northern Finland. Okay. So these are going to be, okay, this meeting was in a series of other meetings. First one was held in Capri, Italy, and then Hawaii, Australia. These are all kind of interesting places also from the point of view of astrobiology or bioastronomy. And now this meeting was in Iceland. The place for the next meeting I think is still open, but there are interesting places mentioned. Now, in that larger meeting, one's kind of biased in one's own interests and also somewhat on the background. So I'm not going to go through all the details about astrobiology because there are lots of kind of general stuff in this meeting, but then there were some interesting things, and I think these are the points that I would like to focus on, each one about one slide here. And then I'm going to give also a small summary of our field trips. We had 2 field trips, one mid-conference afternoon trip and then a 5-day Northern Iceland trip. Okay, the topics I've selected here where I heard something really new and I think kind of revolutionary were planetary formation, giant telescopes, common ancestors of smaller bodies in our solar system, Europa, Mars, and Titan, and then also about the limits of life, and a little bit about SETI, where and what are they. Okay, planet formation. There are several interesting issues I've always tried to mention if these were brought up usually in one talk. Planets seem to be classified into solar system planets seem to be classified into 3 different groups. Rocky planets like our Earth, and then gas planets and ice planets. I think that separation into gas and ice planets, that seems to be now pretty well based. And there are models of how to create these kind of systems under different distances from the star and different surface density on the disk. It depends a lot on the surface density of the disk. There are also talks on planetary systems and binary systems. And Alan Bosch said that Jovian planets can be found in principle in binary systems if the separation of the 2 binary stars is smaller than 25 AUs. Means that you have the accretion disk around the star that are suitable for formation of Jovian planets. Also, in binary systems you have tidal forces, much stronger tidal forces than the single star systems, and these tidal forces trigger planetary formation. So it seems to be slightly different from ordinary planetary formation. Okay, then about our own Earth, it was kind of interesting to bring up that suitably large oceans seem to be important for life. If the whole ocean covers the planet, then you get no weathering, and things get almost as dull as if you don't have any ocean. So the 2 extremes are going to cause no weathering, no CO cycles, nothing like that. So for all, it seems like all the important things in life you have to have some large enough oceans. Now, one of the things I've also taught on courses is that comets are primordial. You study them, you know what was like 4.6 billion years ago when Earth formed. But it's important to know that there has been 5 billion years of chemical evolution even in the comets that we see today. So they are not exactly primordial, there's some evolution also there. Then, second thing are these big telescopes. First, the huge ground-based telescopes, which was talked by Hans Inneker. He mentioned several of these extremely large telescopes, overwhelmingly large telescope, and then two smaller telescopes that could be combined. And the problem he was addressing is how to resolve and study Earth-like planets, nearby stars. So the problem is that you have a 30th magnitude object, which is, if you know astronomy, it's quite a faint object. And that's not the only problem. The other problem is that if you want to study the planet, you have to be able to resolve it, like say 10 to 10 pixels. You can see continents or some other details. But another problem is that you have a really bright star, so the brightness of the planet to the star is about 1 to 10 to 10. And then if you want to get a large enough sample to study these, you have to go to a distance of 30 to 100 parsecs. To meet all these requirements, you need for a jogging plant, you need a 30-meter telescope, and for a terrestrial plant, you need a 100-meter telescope. Sounds pretty big. Well, the big size brings huge problems. You have to have really good adaptive optics, or active optics actually. And then you have new kind of problems, and you have to think about rotation really carefully, because that says a telescope, 30 meter or 100, it's going to be a good sail in the wind. Just think a strong wind hitting a 100-meter telescope, that's going to be quite a problem, and also local seeing needs to be good. And third, we're hitting one of the limits, and that is that technology and money are not available at present. Well, one could go off to space. There's a planet called Rayfinder, and the main aim on Rayfinder is to detect spectra of terrestrial planets, and there's a whole bunch of different kind of lines you could see: oxygen, methane, the red edge due to photosynthesis, and CO2. Some of them are in optical and some of them are in infrared. One of the things that I had actually seen by my own eyes, but I had not realized it, how important it is for detection of light, is this red edge. If you ever take a picture of scenery with an infrared filter, near infrared filter, you're going to see all your trees look like white. And that's the red edge that comes there. And what that red edge is the following. If you look at the reflectance, take sunlight, you let it shine on different substrates, and you look at the reflectance, say, goes from 0.1 to about 0.5, and that goes from 0.4 micrometers to about, say, 2 micrometers. There's 0.7. Look at ordinary soil, it increases linearly. If you look at plants, like you see it goes about the same, and then at 0.7 it just shoots up. It's almost a straight edge, and then it comes later down. So detecting this kind of red edge would be an important signature of plant life or photosynthesizing life. And now that has been tested, actually these all have been tested by spectra of Earth from Galileo satellite, and this red edge has been looked from the Earth's shine on the moon. And that actually turns out to be an interesting experiment by itself, because it's so difficult because of the bright contrast between the bright moon and the Earth's shine. And now, if you look at Earth, you could also see rotation-dependent variation, because half of the time you see just a huge ocean where you don't have that red edge, and half of the time you see the continents basically. So you could also get the rotation time. Now, If you put all this up in space, you have a 30-meter telescope in the space. One of the problems is that like the Hubble Space Telescope vibrates about 40 picometers from the edge. You should have vibrations that are smaller than 1 picometer, otherwise the quality of the image degrades too much. And now that means that you should put this kind of spacecraft in the Lagrangian point 2, which means it's behind the moon, or on the moon itself. And now, again, the questions of money and technology, we're talking about timescale about 200 years from now.
Exactly, what is L2?
L2 is kind of an equilibrium point behind the moon in the Earth. It's basically the Sun, Earth, Moon system. It's kind of a stable. Let's see. You have this different kind of stability points. Sun is there. Earth is here. That's one equilibrium point where you have many satellites at L1, and L2 is actually in this system, if you just ignore the moon, it's behind the Earth. I think that's about 1.5 million kilometers behind the Earth. So the sun is blocked completely from that point. That's why the stable point is out there. Apparently.
Did you say stable?
Right?
You can't stable.
Let's say it's certainly more stable point. It's not dynamically really stable. L4 and L5 which would be here would be much more stable, but then you have the sun shining. Here you don't have the sun shining because the Earth calls it, and you get rid of all these.
Actually, there's an advantage of having an unstable point, because then you're free of dust. In the L4 and 5 points,
right,
you have all the dust, of course, because they're stable.
Yeah. Okay, let us look at about biology. I found this question about the last common ancestor very interesting. And there was also discussion about lateral gene transfer. This was brought up in many different talks and different circumstances. The most often shown phylogenetic tree is based on 16 satellite RNA. It looks like this. So there's the last common ancestor. You have bacteria first rooting out or forking out, and then you have this common line, which is the common for archaea and eukarya, and then these two separate later. Okay, so you can easily think that the last common ancestor was maybe something like bacteria. But then you can draw this tree also in a different way, which looks like this. You have the eukarya branch here, you have the bacteria here, and you have the archaea here. And the common root is somewhere down here. Now the problem is where to put the root actually. Where the last common ancestor is. Should we put it there? Should we put it here? Where did it start from? And that seems to be a non-trivial question. Okay, there were one paper and one poster mentioned that RNA world relics are found in eukaryote, are not found in archaea or bacteria, which could suggest that actually eukaryote may have formed independently of these two other groups. Then Nestor mentioned about lateral gene transfer between Dermatuga and Pyrrhococcus, bacteria and archaea. And then there was talk of photosynthesis about the different types, 1 oxygenic and 5 unoxygenic. And it was pointed out that the bacteria are not related to each other. They're different parts of the phylogenetic tree. But there are common things for all these photosynthesis mechanisms is that there are two different basic reaction centers and many different needs for photosynthesis. And what Lucas kind of indicated was that there has been horizontal gene transfer happened at least 6 different times in this photosynthetic organism. Also, it seems like some viruses also hold the same kind of reaction centers. So these were all kind of indications that the simple branching tree, well, it's based on a satellite RNA, the original one. There seems to be lots of lines going across, particularly across the base. So that kind of brings the question of how you really define a species at a unicellular level. Yes, it's a non-trivial thing. Okay, then about limits and other things. Icelandic studies show that there seems to be life in about 120 degrees, but not 300 degrees. This is kind of old stuff, but this limit was kind of a new, I think, quite a strict limit. And then in discussions, there was an interesting question brought up about these extremophiles. Are they pathogenic? Can they cause diseases? And the answer was that we don't know. And that kind of brings up an interesting thing of the microbes in general, is that the microbes we know, they are either the ones that cause diseases, and the ones that we have studied really, but then there are extremophiles. These two groups are kind of studied more than other groups, like more than the ordinary ones that are in the soil, basically, or on your nails, or anywhere around here. These common microbes are not that well known. Then there are some really extreme cases mentioned, like Cyanidium caldarium, which lives in 100% CO2, almost pure ammonium. That was an interesting small detail, I think. Europa. There are several talks on Europa and Mars. It seems quite clear that Europa has an ice which is about 10 kilometers thick and an ocean which is about 160 kilometers deep. The main salinity seems to be caused by magnesium sulfide. It should be 4 down there, so that's about maybe 100 grams per liter. It's not an accurate number, but it can be, say, up to 300, or it can be down to 1 gram per liter. And that comes from the conductivity also. You have energy sources inside Europa, like radioactive decay, which is also called by tidal. Sometimes the formations in Central Europa. And you have also oxygen forming possibly on the surface from hydrogen peroxide. Formaldehyde seems to be available, so all the basic ingredients for life could really be up in Europa. Now, one of the questions that comes up is how you define life. If you go to search for life, how you can tell that the stuff you have found is life or not. It's a naive thing to assume that life is going to be identical to the one we find on the Earth. And that was kind of a big question mark that was, I think, left open there. It was also brought up in the talks about Mars, on where life can hide on Mars, what kind of experiments we should do to look at released hydrogen, for example, things that the Vikings never looked at. And also the methane that was just detected in Mars, that's quite interesting. It could be caused by either life or volcanic activity.
Excuse me. What is the nature of particle bombardment here? What is the nature of particle bombarding?
These are
cosmic particles?
Yeah, particles from the sun and in the Jupiter's belts. Okay, and then SETI. 1 hectare telescope. There are bigger plans now. kind of big array that looks at the sky all the time. 350 telescopes, radio telescopes, each 600 meters. We have 65,000 baselines. So they're monitoring the whole sky. They have now built so far 3 telescopes. They're now building more. It's privately funded. This was brought up by Frank Drake in his talk. And one of the interesting numbers that he came up was, when are we going to hear from those other guys? If there are a million other guys, like Sagan thinks, or Sagan thought, with that telescopes, we should statistically have contact by 2016. If there are only 10,000, like Drake thinks, then we should have contact by 2025. And by 2033, if we have not had any contact, then we can argue that we might be the only ones. So that's assuming that once you have evolved your radio transmission systems, they keep on going. But if we're looking at the way we're heading right now, and we have been a radio planet for the last 50 years, lots of radio broadcasts are going actually to cables, no TVs, no cable TVs. They don't need radio that much anymore. Satellite beams are very low powered. They're like 15 watts from these intercontinental links, and they're really faint, really low power. And it may be that Earth is going to become radio silent in another 50 years. So maybe that's actually the wrong way to look for SETI. But it's important still to look in all possible ways for other civilizations. One thing that we're still producing is waste radio, energy, radio emission, and that's something we could also look for. Another interesting thoughts were to look for Dyson spheres. These are basically civilizations that have encapsulated the whole central star. They should be found in infrared, if anywhere. Okay. Every meeting has a couple of catchy expressions. One of them means what life needs. It needs energy, water, and schnapps. These seem to be all from NASA. It's actually quite a nice word because it makes it easy to remember. And then a word, Abstart.
What is schnapps?
Schnapps is an important ingredient that life needs. Carbon, hydrogen, oxygen, so on. But it makes it easier to remember. Okay, then Abstar was also defined, and a Finnish name could be Elotahti, and it's defined for Darwin and TPM. So it's defined as a star that has a habitable zone, which is dynamically stable on a time scale comparable to the time scale of global biosignature production. Depends on what you're studying. This time scale could be 2 gigayears or 3 gigayears. That's for just life to form, or say plant life, and this is for civilization to form, so you could have different time scales here. And then it also should have a habitable zone that's static enough on the same time scale, and also high enough in time speed in the central star so that terrestrial planets can form. Then every meeting also has this yes and no argument. Somebody says yes, it's this way, and others say no, it's not that way, and then you hear the other talk and the same argument goes on. Now I'm bringing up three cases here. One was Lake Vostok. One person said there's no life there, all the detections have been contamination. And then there was another talk that says yes, there's life, it's not contamination. And the arguments on each side, well, I kind of tended to go on that side in these arguments, but it's maybe a personal opinion. And then about the oldest cyanobacteria, fossils. There were claims that they could be graphite. basically dried graphite. That you get similar kind of things if you take graphite, hydrate it, dehydrate and rehydrate it again, do this cycle several times, you get similar kind of layered looking structures as we see in these cyanobacteria fossils. And the question was, are these fossils real or not? And there was some lively discussions about that. And then one of the things that I found interesting, very interesting, is that when cells die, the level of chirality begins to reduce. It doesn't go down immediately, but it starts reducing. Yeah, homochirality. So, I have another real argument for that. Why does it go down?
Is there any experimental evidence for this, or is it only theoretical kind of speculation?
No, he claimed that if you look at all the fossils a few 100 million years ago, you don't see any chirality there. But how fast that happened was not meant to me. That it started to happen immediately after you die. Not you, but a living creature dies. How fast is that process?
But isn't it the same as racing dating?
Yes, I guess so.
Yeah.
So it's a temperature-dependent decay, which can be used for dating if you're fairly sure about the temperature.
Yeah, yeah.
But in practice, you're not. That's my understanding.
Okay, then some alternative theories. Accretion discharge around stars, ones where planet forms from, are usually thought to be quite warm in the center, so ice is evaporated. But there are also thoughts of cold accretion discharge where you have ice on the distance, 180 from the central star. And then an interesting, very provocative thought was all you need is hydrogen cyanide. You can create all the stuff after that. And it was interesting. I mean, he had interesting arguments there. You can create nucleic acids, and you can create also amino acids from that stuff. And hydrogen cyanide is common in space. And then we had two field trips. Just a couple of pictures from these field trips. Mid-conference was an afternoon, long afternoon trip, and then a five-day post-conference trip. Iceland, the home place for Icelandic Parliament in the 1100s. It's still an important place. Some people say this is where Europe and America separates, but there are other places also where they say the same thing. This seems to be like maybe the place. Pretty high cliffs here. There was actually yesterday a TV program on the same area on Finnish TV showing the thing underwater. Just close here in Thingvallavatn, underwater. You see similar kind of structures there. And that's the thing better. Geysers. We went to a geyser field, and this is the one that's most active there. And that's interesting from the point of view of Mars, because there was just a recent news claiming that Mars is still volcanically active. So Mars Olympus may have erupted last time only a million years ago, which is geologically really recent. So you could have also something a little bit similar to this on Mars. Then, on the northern field trip, we went to areas that really looked like Mars. It's cold. Well, it wasn't that cold, but it's quite cold. It's barren, basalt fields. I did bring here some interesting stones. Bringing back some of the stones to our son, who's going to be a geologist in about 20 years. He was very interested in this one stone that floated on the water. Just put it in his boats. You can bring it here tomorrow just for curiosity. Look at some of these fields there, and you just stop on that field and you think that this is something like I could see on Mars. And I could just take a satellite image and make a comparison with one of these. And there's some ice there, and so you can guess that I'm not on Mars or this kind of thing. some humans from scale, and some people went down here for swimming. But you see these kind of similar kind of things, some of the crater edges where you see kind of ice melting. And then there are also nice signs of these kind of catastrophic floods. You can see these huge areas that were flooded, and some of them were still. You can see rivers flowing. I think this was Gulfos. From a different perspective. And then these were in central Iceland, driving with the road. AB2, the most beautiful mountain in Iceland, voted by the Icelanders, where the Queen of the Falls lives. Apparently quite a challenge to climb up that mountain. It's a nice volcano. I understand that was about the level where the glacier was, so it just made it after the glacier during the last ice age or so. Smaller volcanoes, so that got partially humid there, but there's real steam coming from the ground, and you can see some sulfur here, yellow color. All kinds of interesting basalt formations. It would be just fun to go there and just take lots of photographs and study these just from a mathematical point of view. Then we had a small walk up on the glacier. Actually quite a walk. The glass is not shown here, but you have to look carefully where you step. And that's going even further up. And we ended up walking, I think, up to these rocks here to see some hot springs. These are hot springs from a different area, smelling like rotten eggs. Interesting smell, and water feels like soap. Extremophils living in these pools. And some people in our group also collected some samples from some of the crater lakes. Having a short lunch break there. So we were about 20 people in this Northern Iceland excursion. And this one, Mars? No, it's Iceland. From the airplane after leaving Keflavik. It's hard to tell from a photograph. I mean, you can see a chain of volcanoes here. It looks almost like Mars. The thing you can find in Mars, at least so far, are flowering plants.
Thank you. Thanks, Harry, for the very nice recap of this meeting in Iceland. Questions, please. Or other observations, because there were a few participants at that meeting, of course, who are also here now. Any additions? Okay, I guess we have to wait for...
I would like to speculate a little bit about this red edge detection, because like this is of course very